Welcome to UVM's first World Water Day, which is very exciting. So World Water Day is typically held on March 22nd, and it began in 1993, and it's an annual UN observance focusing on the importance of fresh water. World Water Day celebrates water and raises awareness of the 2.2 billion people living without access to safe water. It's about taking action to solve the world water crisis. Every year, UN Water sets a theme for World Water Day, and this year is glacial preservation. And while we currently don't have any glaciers here in Vermont, we are putting our own twist on the theme and focusing on warming winters and the impacts in the Northeast. From climate change to urbanization and demographic changes, water supply systems face numerous risks. The World Economic Forum's Global Risks Report in 2025 lists natural resource shortages as the fourth biggest risk over the next decade. That's why raising awareness on conserving and protecting fresh water for everyone on Earth is vital, especially as the world looks to find and implement solutions. So thank you for all coming today, and I'm going to pass it off to Anna from Lake Champlain Sea Grant and the Water Center to kick things off.
Yeah, awesome. Thanks. So before we get into the keynote, I just want to say one of the goals of this event, in addition to learning from a really great keynote presentation, is to get people that are working and are curious about water resources in the area together. So I encourage you all to chat with people at your tables, see what you all are doing in the field, and also check out all the tables across the room. Today we have a couple great organizations with us, both in the front of the room and in the back out there. So we have the Vermont Rural Water Association, the UVM Spatial Analysis Lab, the Rubenstein Ecosystem Science Laboratory, the Adirondack Watershed Institute, Northern Woodlands Magazine, Lake Champlain Committee, and the hosts at Lake Champlain Sea Grant, the Water Resources Institute, and the Vermont Water Center up here at this table. And if after today you're not watered out from these presentations, tomorrow in Plattsburgh, in the town of Plattsburgh in New York, there's another World Water Day celebration hosted by the Lake Champlain Basin Program that we'll be at, and I think a couple of the other tables will be at. So check that out if you're in the area tomorrow. And then with that, I'm going to pass it over to Beverly, who's going to introduce our speaker.
I want to start by thanking Anna Marchesholt, who you just heard from, and Hannah Fisher, who started us off, for organizing this event today. It is pretty noteworthy that this is our first ever World Water Day event at UVM. We've been celebrating Earth Day for many years, and we decided we need to start celebrating World Water Day. One of the things that we are trying to do at UVM is elevate our understanding of the importance of water and elevate UVM's image and presence as really on the cutting edge of advancing water-related research, scholarship, teaching, and so on, and partnerships. And so I want to thank those of you who are coming and staffing tables today to get the word out about your work within the community. And invite you to just continue to engage with us as community organizations doing this important work of water out in the world. Raise your hand if you're a current UVM student. Awesome. How about a UVM researcher, postdoc, graduate student? How about someone who advises UVM on sort of research to translation, critical intellect, any professors in the room or retired professors in the room? Yes. All right. So thank you all for being here today. It's really great to bring this group of people together, and we hope that what we're starting today becomes a tradition at UVM of celebrating this important resource of water and UVM's contribution to building partnerships and advancing research, knowledge, and education. It is my pleasure to introduce our keynote speaker today, Dr. Alix Contosa. Dr. Alix Contosa. Alix is a research associate professor with the Institute for the Study of Earth, Oceans, and Space at the University of New Hampshire, where she also serves as the assistant director of the Earth Systems Research Center. She is an ecosystem ecologist who focuses on changing winters and their effects on ecosystems and people. Her graduate work at the University of New Hampshire examined season-specific microbial and biogeochemical response in soils to warming climate conditions. She is also an expert on nitrogen dynamics in soils, a key constituent of soil ecological processes. More recently, Dr. Contosta's research with others in the Northeast has led to an improved understanding of what she and her collaborators have referred to as winter weather whiplash, winter weather whiplash, which they define as, and I'm going to read from the abstract of one of their papers, a class of extreme events in which the collision of unexpected conditions produces a forceful, rapid, back and forth change in winter weather conditions that induces an outsized impact on coupled human and natural systems. And I'll just remind you that yesterday, many of us were sitting outside in t-shirts. This morning, we woke up to snow on the ground. And this afternoon, it's sunny and getting warmer again. And so Dr. Contosta's work on this whiplash effect that we are increasingly seeing is very pertinent to the reality that we are facing and very pertinent to the theme of this year's World Water Day. Dr. Contosta's research has broad implications for soil health, greenhouse gas emissions, and water quality. She is a collaborator at the Hubbard Brook Research Forest in New Hampshire, a long-term ecological research site and home of some of the most important work on forest ecosystem dynamics that's been conducted in the world. She has been a participant in the Northeast Snow Survey Feasibility Study, or NESS, examining the need to develop improved winter monitoring across the Northeast, an effort that Josh Bennis here at UVM has also been spearheading here in Vermont. And she is the co-lead of a newish graduate training program at the University of New Hampshire, funded by the National Science Foundation to train graduate students to better investigate and understand the interwoven impacts of climate change and climate seasonality on Arctic natural and human systems. So it's our great privilege to welcome you here today, to thank you for doing the drive over from New Hampshire to help us launch what we hope will become a long tradition at UVM of celebrating water on World Water Day. And with that, I will turn it over to you, Alix, for your talk on vanishing winters, lengthening springs, and ecosystem water and carbon cycling in a warming world.
Can you hear me okay? All right. So thank you so much for having me here today. I've had a wonderful time so far today getting to know some of the students that are here at the University of Vermont, seeing the Jericho Research Forest, touring some of the sensor infrastructure there, having lunch, and I'm happy to also give this talk. I'm going to tell you about this aspect of my research program that Beverly mentioned that's really focused on trying to understand how changing winters and shifting seasonality impact forest ecosystems. I do a lot of work studying the carbon cycle, but because this is World Water Day and water is fundamental to many parts of the carbon cycle, I'm going to focus more on the water part than the carbon part. Oh, this one. Nope, not that one. Okay, great. Okay, so why winter? Why am I focused on winter as a topic? Well, I actually love the winter season, which is not popular in all spaces. It may be popular in Vermont because a lot of people in Vermont really enjoy winter, but I actually grew up in Philadelphia where it does snow, but less and less than it used to. And I never had the experience of being in a snow-covered landscape, a natural landscape, until I moved to New England in my 20s. And it was really kind of a new experience to me to be out in the woods, seeing trees without their leaves, seeing really subtle colors in the bark that are impossible to notice during the summer. Also, you know, seeing winter as a playground. I learned to ski in my 20s, and this picture of me is in Grafton, Vermont, 20 years ago when I was trying to learn how to skate ski, and I did a lot of falling, which anyone who's tried to learn how to do this knows. So winter to me is something that's personal, right? It's a time to be outside, a time to play. But winter is also a season that has really captivated my imagination since I was a graduate student. So I did my graduate research at the Harvard Forest down in north central Massachusetts. And as I was trying to find a research topic for my dissertation, I was learning a lot about how there are active microbes in the soil beneath the snowpack. There's liquid water. There are roots that are alive. That beneath snow ecology was really fundamental to the functioning of forest ecosystems, but we just didn't know a whole lot about how it worked. And so I was really intrigued by that, thought it would be a really interesting topic for my study, for my dissertation, and it's something that I'm still doing to this day. And in this picture, I'm walking out of the woods, dragging behind me a sled that's loaded with soil samples that my student technician, Olivia Saunders, and I had pulled out of the ground. So this is work that I started a long time ago, and I'm really happy that I'm still doing it. But winter is not just exciting to me as something that I find a lot of joy in personally, and that I'm also really intrigued in for the science that I do. It's also a really key period for the ecology, the economy, and the culture of the northern forest region that we live in, both historically and currently. Winter and the snow that we receive is very critical to supporting the winter recreation and tourism-based economy, and also resource extraction. There's lots of sites that we can only access during the winter to do logging without doing a lot of damage to soils and streams. And I know I'm in Vermont right now, so I don't have to tell you about the importance of maple syrup, right? But the snow cover that sits on top of the soil is really important for keeping the soils unfrozen, for keeping roots alive, for keeping liquid water. And that's really important to the health of maple trees throughout the year. And then when we start to have our freeze-thaw cycles at the end of winter, the sap also starts to run. So winter is very important, not just to me personally, but it's very important in a lot of dimensions. And winter is a time that's changing. So here is a map of the contiguous United States. This is a figure from Climate Central, and what it's showing is how much winter has warmed since 1970, county by county. And areas that are lighter have experienced less warming, and areas that are darker have experienced more warming. Did you want to do with this? Okay. And you might notice there's some really dark red blobs on this map in the upper Midwest and also in the Northeast. And these are two areas where we've seen the most rapid winter warming in the nation. So we know that winter is getting warmer, but I think it's important to consider how it's getting warmer, because it's getting warmer in a particular kind of way, right? Yes, we're seeing warming temperatures, but we're also seeing temperatures warming above freezing, right? So we're losing the cold. So these two figures are from a paper that my colleagues and I published a few years ago that was aiming to try to understand how winters are changing across the northern forest and what those changes mean for ecosystems and for communities. We divided the study region into 3 subregions, really just for ease of interpretation of the data. But the panel on the left is showing you the number of frost days. So that's days when minimum temperatures are below 0 degrees Celsius, below freezing. And you can see these trends over time of fewer and fewer of these days below freezing, right? The lines are trend lines. And then the map on the right is showing something similar, but here we're looking at the rate of change in this loss of snow cover days in days per decade. And so any dot that's red is showing a decrease in these number of frost days, and the bigger dots are showing a larger magnitude of change, right? So you see, looking at this map, there's a lot of red dots. We're losing the cold. And that's important that we're losing these temperatures below freezing, because that affects the phase at which precipitation falls, right? So if you have cold temperatures below freezing, you're more likely to have snow. And if they're above freezing, you're more likely to have rain. And this is one of the reasons why we're also losing snow, right? So this is a similar suite of figures, only this time I'm showing the number of snow-covered days. And we see again that there's a decrease in the number of snow-covered days, and this is any day where snow depth is above 0, right? So this is a very liberal definition of snow-covered day. So we see this loss of snow-covered days across the region. And this loss of cold temperatures and this loss of snow really means that the winter season is getting shorter. And by that, I don't mean that the months in the calendar are changing, right? So winter is sometimes thought of as the number of days between the solstice and the equinox, or the months of December, January, and February. And those are two ways that we often think of winter, but winter is also a period of the year where we have cold temperatures, at least in this region, cold temperatures below freezing consistently, and we can expect precipitation to fall as snow. And that period of consistent cold temperatures is growing shorter, right? So we see that we're losing about 3 weeks of winter over the last century across the northern forest region. And that includes a later onset of winter and also an earlier end to the winter period, particularly in the more eastern end of the region. And these trends are projected to continue through 2100. So these two graphs are from a paper that my colleagues and I published a couple of years ago that were projecting, among other things, maximum and minimum temperature over a historical period, in this case from 1980 to 2005, and then looking into the future under two different greenhouse gas emission scenarios, a lower emission scenario and a higher emission scenario. So the gray and black lines are the historical period, and then the blue line is the lower emissions scenario, and the red line is the higher emissions scenario. The dark bold lines are the model ensemble means, and then the squiggles behind them are individual models. But the key take homes from these two figures are that both minimum and maximum temperatures have been increasing and are projected to continue to do so. And if you look at the increase in minimum temperatures under the higher emissions scenario through the end of the century, 2100, you start to see that there are times when, again, minimum temperatures no longer go below freezing, right? So we're losing cold, and we're losing particularly cold temperatures below freezing. Okay. But we know that warming is not just confined to winter. We know it's happening in other seasons. So these two maps are showing change in seasonal temperatures by state from 1896 through 2020. These are maps that are produced by NOAA and the US EPA. And so instead of having county level data here, we have state level data. But you can see that, as before, we see big increases in winter temperatures, particularly in the Northeast and in the upper Midwest. But we also see warming happening in spring. We see increasing temperatures, again, in the region where we sit. They're just not as pronounced as what we're seeing during winter. And these warming spring temperatures can lead to certain things happening, like earlier green up. So this is a figure from a paper that came out about 10 years ago showing the day of year that bud burst is happening for red oak trees at the Harvard Forest. So the same place where I did my PhD research down in central Massachusetts. And each of these individual dots is individual trees that someone went out and looked at and decided, okay, the buds are bursting on this tree, meaning that springtime is sort of beginning in this forest. And even though there are early years and late years over this period of record, overall you see a trend towards earlier bud burst and earlier spring onset. What I'm very interested in is not just winter and spring, but this in-between period, this vernal window from snow melt to canopy closure. So the vernal window period is this period of time after the snow has disappeared and before the forest canopy, especially in a deciduous forest, has gone through these key phenological phases of bud burst, leaf emergence, leaf elongation, and sort of full leaf out and canopy closure. We're in the vernal window right now, right? So the snow has melted, at least in Burlington, right, this morning. Not so much when we were out at the Jericho Research Forest. But it's this time of high light in the environment. There's no snow on top of the soil. There's no ice on rivers and streams. And you also don't have a closed forest canopy. There's a lot of light coming in to the system. And this is a period of high ecological opportunity. It's not an accident that spring ephemerals bloom during this period underneath the forest canopy. They take advantage of this high light environment. But this is a period that is changing in its timing and in its duration. which is really interesting to consider from the standpoint of water cycling in our ecosystems. So one of the first examples that I saw of how the vernal window is changing was at Hubbard Brook, which is a long-term ecological research site in the White Mountains of New Hampshire, and it's a place where I do a lot of my research. This paper came out in 2012, and what it's showing is year on the x-axis and then the day of year on the y-axis. In this case, the day of year when the snowpack disappeared over about a 55-year period. So at the beginning of this record, the snowpack melted around April 22nd, Earth Day. And at the end of this period of record, snowmelt is happening April 7th. And so the snowpack is disappearing 15 days earlier over this entire period. And then we look at leaf out and see how that's changing. So this graph is set up in the same way, but instead of showing the day of year that the snowpack disappeared, I'm showing the day of year that the forest canopy was nearly fully expanded. And we can see that this is also happening earlier. So at the beginning of the record, you have full canopy closure happening May 28th, and at the end of the record, it's happening May 21st. And so we're having canopy closure occurring around 7 days earlier. When you look at these two phenomena together, you see that while both snowpack is melting out earlier and leaf out is happening earlier, the rates of change of these two processes is not the same. Snow melt loss is happening at a faster pace than green up. And so you have this overall lengthening of the vernal window by around 8 days. And there are lots of reasons why this is happening. Here are some. So snowmelt timing is primarily driven by temperature, right? So if you have a warm winter, it means that you have probably less precipitation falling as snow. And you also probably don't get as deep a snowpack, and that shallow snowpack melts out earlier, right? So snowmelt timing is largely driven by temperature. And leaf out timing is driven, yes, by temperature, but also by other things, by photoperiod and by dormancy requirements and chilling requirements. So many of the trees in our northern forest ecosystem do respond to warming temperatures in the spring. They accumulate growing degree days, but they also are hardwired not to leaf out too soon, right? Before they've met some of their dormancy and chilling requirements and before light levels are high enough. And the reason is that, trees don't want to leaf out too early and then end up encountering a spring frost that could be really damaging to new tissues. And so no matter how warm late winter and early spring gets, trees just can't respond fast enough. And so we see this overall lengthening of the vernal window driven by different controls on snowmelt and leaf out. And these different rates of change in snowmelt and leaf out elongate the vernal window with impacts that I would argue are not very well understood. And so, the objectives of the research that I do around this topic are to try to understand how the timing and the duration of the vernal window is changing, and then understand the impacts on water cycling, carbon cycling, both during the vernal window and also during the ensuing growing season, really trying to understand what some of the legacy effects might be of a longer vernal window on water cycling, on carbon cycling, and the growing season that follows. So I'm going to spend the rest of my talk telling you about this work. Okay. Sip of water. So first, I've spent a lot of time trying to understand how vernal window timing and duration is changing, and have gone about this in a few different ways. Initially, we did an observational analysis that used ground-based observations across the state of New Hampshire that included air temperature, snow depth, soil temperature, and soil moisture, and combined those with remote sensing data, largely of leaf area index, because we wanted to try to understand the start and the end of the vernal window. And so to do that, we needed to know, when does snowpack disappear and when does leaf out happen? So we can use these satellite-derived
data on leaf area index to know when the forest canopy is closing. And this map is just showing the location of all the sites. And I'm going to skip to the results and show you what we found from this initial work, which was really that the vernal window is longer following warmer winters and reduced snowpacks. So these two figures are showing similar things. On the y-axis of each, we're looking at vernal window duration, the number of days between when the snowpack disappeared and when the forest canopy leafed out. And what we were trying to do in this analysis was understand how changes in antecedent winter conditions might be affecting the timing and the duration of the vernal window. We know that winters are getting warmer, and we know that we're losing snow. And so we decided to try to plot vernal window duration as a function of antecedent winter coldness, which I'm showing on the left, and we quantified that as cumulative freezing degree days, so days below 0. And on the right, we quantified winter snowiness as the amount of snow water equivalent that was on the ground at the onset of spring melt. And the different colored points on the graph are just different years in the analysis. And what we found is that if you have a really cold winter or a really snowy winter, you have a really short vernal window, a very short time between when the snowpack disappears and when the forest canopy leaves out. But if you have a really warm winter, or you have a winter that wasn't very snowy, you have a much longer period, right? The vernal window encompasses many more days. We expect to have warmer winters with reduced snow cover in the future, and so we expect to have these longer vernal windows. So that was our observational analysis. We also did a model-driven analysis using downscaled climate data to simulate the vernal window, both historically and into the future. I don't have time to get into a lot of the modeling details. We can talk about that after. But for the sake of brevity, I'll say that we used locally downscaled climate data from the localized constructed analogs. And these are data of temperature and precipitation to do two things. We drove the UNH water balance model to simulate snowfall, snow accumulation, and snow melt. So that helped us to understand the start of the vernal window. And then we ran a thermal time phenology model to estimate green up. When does the vernal window close? And I will show you what we found. Okay, so this figure is showing our whole study domain. So we're focused on the northeastern United States and parts of eastern Canada. And this is showing vernal window duration over our historical period. So this is 1980 to 2005. Areas that are in light yellow have a very short vernal window, and areas that are in red and orange have a longer vernal window. And then these areas that are to the southern end of our study domain that are gray have no vernal window because they don't have any snow. They just have a long dormant season. And so historically, across our entire study region, we have a vernal window that lasts 46 days, so about a month and a half. Then if we look at the end of the century under a lower emissions greenhouse gas scenario, we see that the vernal window starts to get longer, right? So over that and the entire region, over that, that time period, we see the vernal window get longer to be 61 days. And if we look at our higher emissions scenario, we see that the vernal window gets even longer and increases to 74 days. And you may also notice that the gray area at the bottom of the map also starts to get bigger, right? So we are starting to lose areas that have a vernal window because they no longer have snow cover. So this elongation of the vernal window may continue through to 2100, and some areas of the Northeast may lose their vernal window due to the absence of snow. So this is something that is expected to persist into the future. Okay, so what are the impacts, right? So why care about this, right? So one of the things that we've been working on is trying to understand the impacts on water and carbon during the vernal window period, right? So what's happening during this period between snowmelt and leaf out? And I'm going to give you one example, and it's a water-based example because this is World Water Day. So we're trying to understand how changes in vernal window timing and duration affect spring hydrology. So I'm just going to show you a schematic of what we think this looks like. So here, this picture is showing the transition from the dormant season, the winter, through the vernal window and into the growing season under sort of historical normal conditions. We have a dormant season where deciduous trees don't have leaves, there's snow on the ground, our rivers are in a low flow state. Then as we start to move into the melt period, we have a lot of that snow melt water moving into our rivers. We experience really high flows. Most of the highest flows of the year occur during this period. We're in the vernal window, right? And then as we accumulate warmth, as we accumulate light, then trees go through bud burst and leaf out. And the vernal window ends as we move into full canopy closure and we get into the growing season and into sort of medium flow conditions in our rivers and streams. We have a longer vernal window. The timing of these things starts to shift, right? So our snowpack disappears earlier. We have less meltwater moving into the system to result in these high flows. And bud burst is also happening earlier, but it's not moving as far to the left, right? Because we know that this advancement in green up timing is not happening at the same pace as snowpack disappearance. So what impact does this have on spring hydrology in our northern forest system? So one of the ways that we went about doing this was looking at changes in center of volume timing. So the center of volume is the date when about half of the flow for a year has taken place. And this graph is just showing an example of what this looks like. It's not for a river around here. This is actually the Yellowstone River. And what it's showing is daily discharge over the course of a year. And the center of volume date is when, half of the flow that is moving through that river has taken place. And this is for, two different periods, one in the 1950s and one in the 1990s. And so that dotted blue line is showing the center of volume date in the 1950s. And then in the 1990s, it's becoming a little bit earlier. And that's that dashed brown line. That's just a visual example of what this looks like, but we wanted to understand how the center of volume timing would be changing as the vernal window gets longer. And so to do this, we first had to understand how much of our study region, which again is the northeastern US and parts of eastern Canada, how much of it has snow and how much of it is snow-free. So this is showing percent area that's snow-free over our historical period and under two different greenhouse gas emission scenarios over time. Starting in 1980, we have our historical period from 1980 to 2005, and then moving into the future. And as we move into the future under different projected scenarios of climate change, we start to see reductions in snow cover. Once we have that, then we can start to look at how runoff center of volume timing is changing. And so this figure is set up in a similar way where we still have year on the y-axis, but the x-axis is showing the center of volume date, right? What's the day of year when half of the flow has occurred? And this is the pretty information dense graph, but what it's showing are these brown lines on the left. This is where there is no vernal window. Historically, which is sort of the orangey line, and then in the future, which is the browner line. And you'll see over time that the center of volume date isn't really changing when there is no vernal window. But when there is one, either historically or moving into the future under a lower greenhouse gas emission scenario, you see that it's becoming earlier, right? We're seeing earlier timing of that peak flow when most of the water that has moved through the system has occurred. And then if we look at our higher emission scenario, we see that that's even more pronounced, and that timing of center of volume, the timing of that, sort of key spring hydrologic transition is happening earlier and earlier in the year, and is starting to line up with areas where there is no snow. Areas where that timing of peak spring flow is tied to rainfall and not snow melt, right? Another way of looking at it that maybe is a little bit more intuitive is just by looking at how important rainfall and snow melt are in center of volume timing. right? So this is what this figure is showing, that over our historical period and under our two different future greenhouse gas emission scenarios, what's the relative importance of rainfall or snowmelt in driving the timing of center of volume? And when there is no snow, we see the importance of rainfall. And we see it increasing in importance as we move into the future under different greenhouse gas emission scenarios. And the trend is flipped, or the pattern is flipped, when the vernal window is present. So when we have a vernal window, when we have snowmelt, then we see how important that is in driving peak runoff timing. Okay, so why care about this, right? What are the implications, right, of these changes in spring hydrology? Well, here's a couple. Loss of winter snowpack and a shift to winter rainfall might change the way that water moves through our systems, right? So this loss of snowpack means loss of water storage on land. Snow is water, right? I mean, it's obvious, but when we have a winter snowpack, it can release that water really slowly into soils and allow for groundwater recharge. If we have less of that snowpack and more winter rainfall, we can increase runoff and decrease that recharge. And these earlier high spring flows can also lead to earlier recession into summer low flows that can have lots of implications for aquatic ecosystems. So that's one implication of a longer vernal window and how it impacts the system during the vernal window period, but also interested in understanding these impacts during the following growing season. What are the legacy effects of a longer vernal window on what happens in the growing season that follows? And so I'm going to show you one quick example because I think we're running low on time. But I'm really interested in understanding how changes in vernal window timing and duration affect growing season soil moisture. So this is a nice schematic that explains some of the ways that changes in snow depth, snow melt timing, changes in the timing of spring onset can affect hydrologic cycling. I talked a lot already about some of these pieces on the left, right? We have changes in precipitation, how much snow we're getting, right, relative to precipitation that falls as rain because it's warm. The amount of snow that sits on the ground and then is able to infiltrate into soils, recharge groundwater, changes in surface runoff, right? The piece that I'm going to move into now is really more related to the timing of green up, right? We are having earlier snow melt and also earlier green up, but those two things are not happening at the same pace. We have this longer vernal window period where it's light and warm. There's a lot of sunlight reaching the ground, and that allows for the potential for more surface evaporation during the vernal window period. And then when we have earlier green up, we have trees that are taking water out of our soils through transpiration, right? So there's more potential for water loss from our systems. And so what we're trying to understand is how changes in vernal window timing and duration then might affect growing season soil moisture. Okay, so one of the ways we've been doing this is using ground-based observations across our statewide sensor network, so the same network that I started out with, but here I'm just focusing on a few sites where we've made continuous measurements of snow depth, soil microclimate, things like soil temperature, soil moisture. We measure soil respiration, or how much CO2 is coming out of the soil. And then we are supplementing these continuous ground-based measurements with canopy phenology. So the timing of when bud break happens, when leaf emergence happens, when the forest canopy fully closes. When did those things occur? And we're using either satellite data or time-lapse cameras of the forest canopy using the PhenoCam network. And we're doing this to try to delineate vernal window duration and understand how that affects growing season soil properties and processes. Again, what are these sort of legacy effects? And I'm just going to skip to one of our results. And this is a paper that we're currently working on. And what we see is that soil moisture is lower during the growing season following a longer vernal window. So this figure is set up so that vernal window duration is on the x-axis and monthly average volumetric water content in surface soils is on the y-axis. And the different colored points are our different sites across New Hampshire, and the shapes are related to how we defined canopy phenology, satellites or cameras. But what you see overall is this trend towards reduced soil moisture when you have a longer vernal window. And this can have implications for carbon, right? So I have carbon in my title, and I'm going to show you one carbon slide. A hypothesis that we have is that reduced soil moisture could affect forest productivity. So this figure is from a colleague of mine, Annie we met, from work he did at the Bartlett Experimental Forest in the White Mountains. And this is showing the length of the vernal window in number of days, plotted against growing season maximum photosynthetic rates, right? How fast can photosynthesis happen? And we see that with the longer vernal window, maximum photosynthetic rates are decreased. This could be from reduced soil moisture, could be from other things, right? It could be related to nutrient availability or root turnover, right? But moisture is one of the hypotheses that we're working with right now, right? So this longer vernal window can lead to reduced soil moisture, and that could impact carbon cycling in these forests during the following growing season. Okay, so just a few conclusions from this talk to sort of end with. So winter is becoming warmer and shorter, and it's becoming warmer in a particular kind of way. We're losing the freezing point of water, right? And that really affects the phase of our precipitation. Does it fall as rain or snow? Is the snowpack able to accumulate? How early does it melt, right? We also see that spring is starting earlier, but this is not happening at the same pace. And this creates a longer vernal window, which can affect the timing of spring high flows, and it can also affect groundwater recharge during the vernal window period. And a longer vernal window can also have legacy effects on the following growing season, can reduce growing season soil moisture with potential impacts on forest productivity. With that, I'd just like to say thank you. Thank the funding sources that have made this work possible, the many colleagues that I've worked with over the years on this, and take any questions that you have.
We are recording your presentation, so when people have questions, I'll run a mic to them so we capture their questions on the recording too. Questions? I'll start with one. Early in your presentation, my eye was drawn to your maps with the number of dots on them, and I think I noticed one dot in Vermont and one dot in New Hampshire. Measurement sites. You did have one a little bit later in New Hampshire with lots of measurement sites. I'm wondering about the value of ground-based measurements in the kind of work you're doing, especially in the context of what you were doing with Josh on advancing this Northeast snow study and on-the-ground infrastructure, what you've shown us on the value of remote sensing products. How important is on-the-ground field measurements and building up sensor networks important for this kind of work?
I think they're very important. So initially, we thought about using not just satellite-based data products, but also more derived data products of snow or soil temperature or soil moisture to try to fill in the holes. And what we found was that often those data products were at such a coarse spatial scale that they didn't necessarily match our observations very well on the ground. And it was hard to know how accurate they were at the spatial scales at which we were operating. For the phenology, the same is true in the work that we're continuing to do. They help you to see really broad spatial and temporal patterns, but in any given year, in any particular place, they may not really capture the reality of the situation that's on the ground. And so the ground-based observations, I think, are really important, both for validating any data that you might be getting from a satellite, and also for understanding sort of more local, smaller scale properties and processes of a system.
Hey, great talk. You are kind of implicitly conceptualizing snowpack as something that builds up, it stays around for a while, and then it goes away and it's all gone. But often in places that are slightly warmer than here, what we see is not just no snow. We see snow, then it melts, then snow, then it melts, and kind of a transient snowpack. So, in your thinking about a vernal window, how does that work in a place that might have a transient snowpack, and how do you think it affects the role of that period from like the last melt of a transient snowpack to bud up? Like, what does that mean for hydrology and carbon?
Yeah, that's a really great question. There's a lot of answers to that. So one is that you may have noticed in some, maybe not, some of the figures I showed, you have a negative vernal window because you have snow melt happen and then green up happens and then you get another snowstorm, right? So crazy things can happen in these systems and they don't always behave. And we are operating under the assumption that we have a snowpack that builds, accumulates, reaches a maximum depth, and then slowly melts. And that's true. That's definitely not always the case. I think the impacts on the system when you have intermittent snow really also depend on what the temperatures are. So when Beverly was introducing me, she was talking about this idea of winter weather whiplash, and that's something that I've worked on a bit. And if you have intermittent snow and it's warm, that affects the system very differently than if you have intermittent snow and it's cold, right? Because intermittent snow cover or no snow cover with cold conditions, maybe you have you hear about the polar vortex and an Arctic blast, you can end up with frozen soil in those kinds of conditions because the snow provides really important insulation to the surface. And without it, with a lot of, with really cold temperatures, you can get really deep soil frost, and that can affect the way that water moves over the landscape, right? So then you get more runoff because the soil is frozen and is acting more like pavement, right? If you have intermittent snow and it's warm, then you have precipitation that's then able to sort of percolate through the system and move into groundwater in a different way. So it's, I guess my answer is it's complicated.
Other questions?
I'm writing a paper about this for one of my classes that relates to world food. Um, would I have your permission in accessing the PowerPoint presentation for this and also and if possible, the sources that went into this just for research purposes?
Yeah. I don't know how that would happen, but I think the presentation's recorded, right? Yeah.
Awesome. Thank you.
Great presentation. I feel like I am not a trained hydrologist, so you gave me a lot of vocabulary to explain what I'm seeing here in Vermont. And I think this is really timely to be able to talk about this during the season that we're seeing it. And I'm wondering, it would obviously be really different, but you were saying at the beginning, winter is shortening on both sides of the season. And I'm wondering if anyone's studying if there's any potential impacts happening in like stick season in water or carbon cycling as well?
That I don't know. It's not a really important area of my own research. I'm interested in expanding into that. I know that a few years back, and one of the inspirations for the initial paper that we worked on back in 2017, one of the inspirations for that was a paper by Irina Creed that was looking at intensification of the hydrologic cycle during vernal and autumnal windows and trying to understand how changes during that movement into the dormant period might be affecting aquatic systems. So that would be a good place to look, but I haven't really visited that literature in quite a while, so I don't have a great answer to that for you.
That's okay. Awesome. Thank you.
Other questions in the room?
With the effects on groundwater that the extended vernal times are having, Have you seen or heard of any agricultural impacts with that, change in groundwater versus runoff?
Yeah, so the groundwater impacts are potential implications, right? I don't know if that's happening. So that's, I think, something important to highlight. That's a potential implication. That's something that I'm very interested in understanding, right? So I think it's, to me, interesting to consider how in the Northeast US, where we are, a mesic temperate system, to consider how snow may affect water availability during the following growing season, because that's not something that I think we're used to thinking about in this region, right? But if you have a low snow winter and it's followed by a dry spring and then by a drier summer, there is this potential for there to be water scarcity, right? Drought and implications for agricultural productivity for sure. And then some of the other pieces that are less related to groundwater, more related to just how changes in snow cover can affect ecosystems. Going back to this idea of the snow providing really important insulation is key, because that keeps soil from freezing. So you could have really cold air temperatures, but if you have a nice deep snowpack, it keeps the soil above freezing. And that means that there's liquid water and that the roots that are in the soil are able to stay alive, right? Microbes are active, they're processing nutrients. If you have an absence of snow cover and really cold temperatures, that's when you see soil frost, and that leads to fine root mortality. It can lead to microbial biomass mortality, loss of nutrients from the system. And so that certainly also can impact agricultural systems in the following growing season, particularly for perennial crops, because they're the ones that are going to be experiencing the perennial crops and cover crops, right? They would bear the brunt of that.
Thank you.
I feel like I might have seen one more hand up there. Anyone else? I want to wrap it up with one last question. Oh, there is another one? Sorry, I'm not seeing. Oh, Craig.
Thanks for your talk, and it was just so interesting to hear about the vernal window and all that that means. But in Vermont, we've had quite a few of these flooding events, mostly in July. But in December 19th of 2023, we had major flooding. And so I'm wondering if you're engaged in any studies, or your colleagues are engaged in any studies of the other side of winter and the volatility of snowpack, sudden snow melt. I mean, is this going to continue to happen in November, December? Because that flooding event was unexpected. I think Beverly could speak to that.
Yeah, it's a great question. And so this is this idea of rain on snow events increasing in the future, right? So we had in that instance snow on the ground already, and then precipitation event that brought a lot of rain. And so then you have this, collision of conditions of a lot of water that's stored in that snowpack that melts out really quickly, and then you have rain falling on top of it, and then you end up with flood. It is something that I'm interested in, and something that Beverly mentioned that Josh and I are working on, the Northeast Snow Survey feasibility study, and that's designed to create a very robust network of stations throughout the region that are measuring variables like precipitation, like snow depth, like snow water equivalent, like temperature at very high temporal resolution, with one of the goals of being able to do better job of flood forecasting, understand what are the conditions on the ground now, and what is the likelihood, given those conditions, that we may end up with floods. It's hard to know if those events are changing a lot over time because they are pretty rare, and so that makes it hard to detect trends. And it also requires that there's snow already on the ground, so it's already been cold, but rain coming in on top of it. And so there may be this sort of period for some amount of time where it's cold enough that we still have snow some of the time, but warm enough that we get rain on top of it. And then we may move into a future condition where it's no longer cold enough for there to be snow, so you don't get rain on snow. You kind of have to have those two things happening at once. So it's an area of interest for me and something that Josh and I are working on creating more robust measurements to be able to predict. It's a great question.
Thank you.
Okay, I was going to wrap it up with a question that might get some people talking after the formal part of this. And that is that there are a lot of students in the room. And I was pretty intrigued when I was doing my research on you about University of New Hampshire's graduate research traineeship in changing climate conditions in the Arctic. So I was wondering if you might close by telling our crowd a little bit about what's happening in training graduate students at UNH around these winter fading conditions. It's actually very apropos for the real theme of World Water Day today, shrinking glaciers. And then I'll turn it over to Hannah and Anna to tell us what's next.
Sure. Yeah, so UNH has a graduate program called Graduate Research Traineeship. It's funded by the National Science Foundation. And our goal is a lofty one, and that's to transform graduate education at the university, to try to train students to be able to bring together multiple disciplines, right? So we have students from all departments, engineering students, students in ecology, in anthropology, to try to bring students from multiple disciplines together to try to understand how to address climate change and changing seasonality in the Arctic, using principles of convergence, which are, integrating across disciplines and also collaborating with communities to come up with solutions. So that's a lot of the work that we're doing, and it's focused on some of these similar themes that I talked about, but really focusing on Arctic specific systems and also trying to train them specifically in best practices for engaging with Indigenous communities, because Indigenous people who live in Arctic regions are really heavily impacted by a changing Arctic and changes in seasonality, which impacts infrastructure, transportation, wild food resources, and ecosystems. So I can talk about that all day. Fun.
Speaking of which, if you are a student in the room and you're thinking once you're done here at UVM, you might want to go on for graduate school, you know what to do in the next half hour or so. Dr. Alix will be here for conversations, and we welcome you to come up and talk about that potential next step in your academic careers. And now I'm going to turn it back to Anna and Hannah to tell the crowd what's happening next. Let's end here with thanking Alix for this really great talk and the launch of our first ever World Water Day at UVM.
Okay, awesome. Thanks again, everyone, for coming. And thank you, Alix, again. So the next part of this event is really more social. We want you to talk with your tables. We have a bunch of tabling organizations here around the room. And so we have about an hour, like 45 minutes to an hour, for you to just talk to each other about what you're learning, about kind of like where to go in this field. And be sure to check out all the tables, all the organizations that are here from across the Northeast. And there'll be time to also talk in a less direct way to Alix. So you can stay at your tables and mingle, or get up and start going to the tables around the room.